Good evening, everyone. Okay, so let's start. Welcome back to Plan 252, okay, transportation modeling. Okay. Some of you haven't submitted a previous assignment also. So those who did not submit it, even if late, no problem. So please submit in Moodle level later. Okay. So just in case. Agenda for today, we will discuss about the following. Okay, so this is what we discussed last meeting. We have group presentation, network structure, and network utilization up to OD matrix. So we will continue that today, okay, about network utilization and then relationship between network structure and utilization. So if possible, we can continue with traditional transport planning, where you will learn also about growth factor, regression, and nonlinear regression. Okay. And at the end of this lesson, I think you have two assignments. And you see in model. Okay, so this is the assignment for network structure and network utilization. And then for the regression, this one is the assignment. Okay. Okay. So let's start. Last meeting, okay, we have discussed about how we can trajectories, yeah, and we can change that trajectory into network utilization. Okay? For example, you can get the flow matrix, you can get the turning flow matrix, yeah, stochastic matrix, and eventually from OD, yeah, or origin destination. Okay, so and this one is the framework, okay, where you can see we divide into two parts. Yeah? One is the network structure here, and then the other part is network utilization. Okay? So network utilization based on trajectory here. Right? So and then based on trajectory, you can create a OD set or a flow set or external set. Okay, and eventually, if you count the elements of the set, you can get the matrix. Yeah? So OD matrix, flow matrix, and later we discuss more about design line matrix, which we can also divide later into part, which is alternative route and substitute route. Okay? And of course, we can visualize this into flow pattern. Now, interestingly, okay, the same in parallel in the network structure, you can start to see there is connectivity between the OD set and the path matrix. Okay? And then you can also see the connectivity between the flow set and adjacency matrix. Yeah? Later, also the external set and external matrix. Okay. So the OD, the traditional OD is just from the source node to the sink node. Yeah. But our definition of OD here is more general than this. Yeah. So, for example, here in this network, you will have A, G, yeah, B to G, A to H, and B into H. That's the only 4 or 2x2 OD matrix. Yeah? But now if you look at this example here, okay, you can start to see that we are going to see, no, we are not just putting that. So we will go, for example, A to C and A to E and A to G. Why? Because from A, if you say that A can go to G, then in here, A can also go to C. A can also go to E, right? The same thing, if you can say that from C can go to G, then that means from C can go to E and eventually go to G. Yeah. So the OD matrix here is more general from all nodes to all other nodes. Yeah, that they can go through the arrow directed graph. Okay. Now from that we can also get the flow matrix. Yeah. The flow pattern here is the visualization of the flow matrix, where we put the thickness in the network of the flow. And so here I have 5 flow, for example. Here I have only 1 flow. So of course, 5 flow is thicker than 1 flow, and so on. Okay. Last meeting, we also discussed about direct link and indirect link. So this is by definition. Okay, so direct link is a link where there is an order sequence of the 2 adjacent nodes. Okay, and based on that, okay, we can also create flow. Yeah? So flow is basically direct link flow with an application of trajectory that pass through the direct link. Now, because we have direct link, that means we have also indirect link. Yeah? Indirect link is a path between an ordered pair of nodes where there is no link connecting the ordered pair. Okay? So I hope you still remember last meeting we discussed about this example. Okay? Can you create a list of all direct link and indirect links if we have these trajectories? Okay? So given this network, okay, you can start to get the direct link and indirect link. Look at the value here in the trajectory. So direct links mean every 2 consecutive, yeah? A, B, yeah? In trajectory 1, A, B, and then B, C, and then C, D, right? Okay, so this is I repeat this trajectory here. And then number 2, I repeat again here. So this one, C, D, A, B, right? So then we can get the direct link with the C, D, and then D, A, and then A, B, yeah? So indirect link, of course, you can get from C here, from C to A, and then from C, B, and from D, B. Yeah. So yeah, we can list this. Okay. Now, based on direct link and indirect link, okay, then you can create OD. Yeah. What is OD? Generalized OD is basically combined. Yeah? Both direct links flow and indirect link flow. Okay, so combine of direct and indirect flow. Yeah, so OD matrix is very important. Later, after maybe after midterm or before midterm, maybe next week, when we discuss about trip distribution. Okay, so in traditional modeling transport, okay, in traffic assignment, trip distribution, OD matrix is the input, yeah, the default input. Okay, and in fact, traffic assignment will produce flow matrix as the output, yeah, OD matrix as the input. So this is the real purpose of traffic assignment, yeah, traditional modeling transport planning. So now in traditional modeling transport, you can create what-if analysis. Yeah, how to do that? You can change the network structure. Basically, you change the network structure. For example, you add more lane, or you add more road, or you can reduce the number of lanes, or you probably want to make certain links disappear from the vehicle's network, but turn that into garden or into pedestrian network, and so on. So that is the change in network structure. Then we want to know what will happen to the new flow matrix output. Okay. So with that, we can start to create, if you know the all direct links and indirect links, so you can get the flow matrix and OD matrix. Yeah? So here is the example of all direct and indirect links of all of this. And then from there, you can see here, these are the trajectory ID. Okay? And here is the direct and indirect links. And then you can put this into OD flow set. Yeah? So, for example, number one, yeah, we have A, B. So A to B here at number one, right? And then we have B, C. So from B to C here, we have number one, right? And then C, D. And so from C to D, we have number one. And then we have AC. So A to C, we have number one. And then AD. So from A to D, we have number one. And also PD. Yeah? So we have number one. So these are the ID. Yeah? Trajectory ID. Okay. And now based on the number of elements, you can get the OD matrix. Okay, so up to here, is there any question? Now, there's a good news. Okay? I created the program for you. Okay, you can go to model in PLAN252. So if you go to model in PLAN252, there is a lab of network structure and network utilization. Okay, let me share the screen with you. Start to see. Okay, so can you see this? So we have the network structure lab, network utilization lab, and relationship. Yeah. So let's go to the network structure lab. You see here. So in here, can you go to this lab? Yeah. Go to model and then go here. Yeah. Lab of network structure. You get it? Okay. So the instruction is here. So easy. Yeah. So you create random network by setting adjacency matrix here. Certain matrix size. So you choose the matrix size, for example, 5. Yeah? And it will, when you generate, click this button, you can generate random matrix. Yeah? So say I have 4 by 4 matrix, I can create here. And of course, you can change this value. Yeah? So for example, I can change this to 2 or 1. Okay, this one becomes 2. Yeah. Every time you change, okay, this network will also change. Okay. So when you click Control button, you can hold this and change that. So okay, you can also add here. Yeah? So you can also add value here to increase or decrease. Yeah? So right click to if you to right click here will decrease. If you to left click in this visualization of the matrix, you can increase value. Okay. Now this is your input. matrix. So this is the basically weighted adjacency matrix. Yeah, weighted adjacency matrix. Now, once you have the input, now you want to know what is the path matrix of this. So you can go to path matrix. For example, this is the path matrix. If you want to binarize the path matrix, this is the binarized path matrix. Okay. So you want to go to binary adjacency matrix, okay, and external matrix, of course, yeah, and binary external matrix. Okay, so you can play around to get the path matrix. Next, you can also go to the next lab, okay, with this network utilization. Yeah. Okay, so when you click this, you can go to this network utilization. The instruction is more complex. Okay, so here you create a random network the same as before. Okay, you can set the diagonal to non-zero. If the diagonal have non-zero elements, so you can set it to 0. Okay, and then create random trajectory, and then we will have the buffer here. Example, okay, this is the input matrix that I have, so I can create any random network. Oh, the diagonal is going to be 0. Okay. So the same as before, you can move this. And once you have this, you can create trajectory. Yeah, there. Can you see this? So this is the random generated trajectory that you can create. First of all, here trajectory number 1 is B to C to A, and from B to C can go to only from B. No, from B can go to A and then go to C, right? So I can create another trajectory here. Okay. So once you create random trajectory and set to this buffer, yellow part, okay, you can test, okay, if the trajectory in the buffer have reached full utilization of the network or not. So you can test, or still underutilized. Yeah? So there are still certain links here that actually have not been traversed by these two trajectories. Okay, so you can keep generating more if you want. Okay, but they generate the same thing, right? To test again. I still have 2 more. Haven't been have no trajectory yet, so you can create another one, for example, and test again. Oh, in that case, if you don't like to have more trajectory, you can manually set your trajectory here. For example, yeah, A, comma B, comma whatever. Is it possible from A to B to C? So let's test if A to B to C. Is it valid? Oh, it's not. It is not valid. Okay, so you cannot use this. So from A to B, you can only go back to A. Okay. So you can only go back to A. So test. Yeah, this is valid trajectory. So you can add. Is it clear? So and then test again. Oh, still have one more link that still not the transfer. So DA. Yeah. So you can create another one. D, comma A. I can see from D to A, and then you can go from there. You can go to C. You can go to B, for example. Is this valid? Oh, no. It's supposed to be invalid if the so D to A to C to B. Yeah. Comma B. Let's test. Oh, this is valid. Okay, so we can add. Now, with this, you can see that the network is already fully utilized. Okay, then you can show the network utilization matrix. Yeah, can you see this? Okay, so you have the network matrix set based on the IDs. Okay, and you have the flow matrix, OD matrix. Yeah, and indirect flow, okay, the alternative flow and substitute matrix. Okay. So easier compared to when you do manually. So what do you think? Okay, so before we continue, okay, I want you to practice this. Is it okay? Uh, can you practice the example here, okay, with 5 trajectories? So you can input this with the network that you have. Let me show you. This one. Okay. So you have this network, A, B, C, D, and only four, and these are the 5 trajectories. Okay, you can input there uh, in the lab, okay, and you're supposed to get this answer. So once you finish, you can show and share your screen. Okay. Yeah. Go ahead, Min. Can you share your screen? Yeah, I think you are. Oh, you can already see.
Is it showing now, sir?
Okay.
So I just input the adjacency matrix.
Right. So
And then
okay. So
the given trajectories. Now the flow matrix, OD matrix.
I think something is missing there. Is your adjacency matrix mean correct? Please check again the slide.
Okay. I'll look on this.
Yeah, I think because your first column is all zeros, so that should not be the case. Irreducible matrix should not have any zeros. Your adjacency matrix. The last column is still zero. I think the network we have is strongly connected, isn't it? So from D, you can go to A and B. From A, you can go to B and C. And then from B, you can go to C. And then from C, you can go to D. There. From C, you can go to D, not to C. Yeah. Okay. That's correct. Okay. So anyway, the network structure does not have because this is in the lab of network utilization. So basically you can just input because we have it. Yeah. Good. Okay. Okay. Is it the same? The flow matrix and the others are the same as in the slide? Is it the same? Can you compare?
Yeah, the indirect flow matrix is the same, the letter L.
Direct and indirect, is it the same?
Yes, sir. The same.
Okay, good. Okay. So anyone else want to share your screen? Yes, Glenn. Mhm.
Hi po.
Okay, okay.
Um, I
We,
kind of did exactly what Vin did.
you get this result. You can go down at the bottom. You can see the, okay, that there. Okay, I think it's
Sorry.
the same, right? 1 to 4.
Yes.
Right. Good. Okay. So at least you know how to use so your tool. Okay. So with this, you can get the assignment later. Okay. Anyone else want to share the screen or this is enough? Okay. Oh, the night missions. Itu. Now we also have okay. When you have the OD matrix, D, right? And this one is the OD matrix, right? And then you have also the flow matrix. You can minus that. Then you can get what we call as desired line or indirect, yeah, indirect flow matrix. Yeah. So this is the line connecting between certain origin and certain destination of the node, okay, okay, where there is no direct links between the origin and destination. Okay. So what is the meaning of this? Yeah. So interpretation is some indirect flow are probably desirable for you to reflect what is the user preference. Yeah. They want to avoid certain road, for example, maybe not not safe enough to pass there, or maybe aesthetic reason. I don't know. Okay, so there is some direct route if available that probably they still use some indirect, yeah, link or indirect path. Okay, we can also think indirect links as in terms of robustness. Okay, that means in the network. Okay, you want to know is there redundancy or alternative route. Okay. So redundancy seems like not optimal, but this is actually very important for the robustness of the network. Yeah. So for example, if there is a network disruption, okay, and certain maintenance or unexpected surge in demand, then this indirect link flow will play very important role. Yeah? So when, remember, L is equal to D minus F, right? So now if L is 0, that means D is equal to F, right? So meaning or the matrix is equal to the flow matrix. That means look like very optimal, but this is actually lack of flexibility and resilience. And this is also almost impossible, unless in the small network. Yeah, in the big network, from any origin to destination will be connecting. That is almost impossible also. Right? So that means indirect flow usually exists. Okay. So now when the indirect flow exists, okay, we can now divide into two. Okay. One, we call this so L is indirect flow. Okay, we can put into two part. Okay, let's call this T is an alternative route link flow. Okay, so this will utilizing indirect link. Okay, while the direct link exists. So that we said this is an alternative because there is a direct link, but the user still use indirect link. Okay, while DC, so symbol C here represent the complement. Okay, that means if they are in T, they will not be in DC. That means this is the, let's call this substitute route link flow. Okay, again the same. It will utilizing indirect links. Okay, because direct link does not exist. Okay, so of course, because they are complement to each other, so we can say that indirect links, okay, we can decompose into two, okay, alternative route and substitute route. Okay, so if you can analyze these two elements, it will help you to identify, okay, where the direct link is actually underutilized or needed. Okay, let's say here. Yeah. So the symbol T here represent alternative route flow matrix. Okay, that means there is no direct link between the elements of this matrix, yeah, between S and T, but the agent still prefer to use indirect link. There is direct link, but they still use indirect flow, yeah, indirect link. So in this case, we said this is an alternative route, okay, because it will give the number of trajectory that pass through indirect route other than the corresponding available direct link. So in short, we can say symbol T here represent indirect flow despite there is a direct path. Okay, so what is the interpretation? So when you see the low value of T, that means majority of the traffic demands will use direct link as expected, right? So, and that means the direct route are effective, yeah, not congested, yeah. So when it happened, that means the direct path being utilized efficiently. So when you have low T value, that is a minimal detour, right? But you can also interpret this negatively. If the value of T is low, okay, that means there is a high congestion, okay, on the direct links. Okay? That means there is no other alternative route. So there is a bottleneck. Okay, so you can also think two-way, in the positive side or in the negative side. Now for the TC, T complement, okay, let's call this substitute route. Okay. That means there is no direct link there between S and T, between the two nodes, origin and destination. Okay, so there is no choice. They need to use indirect link. So, right? So when we say TC here, that means in short, we can say indirect flow due to lack of direct path. So in this case, you want to have a high value of TC. Okay, so a high value of TC indicate significant indirect flow because no direct connection exists between the two nodes. Okay, that means there is unmet demands for the direct links. Okay, so positively we can think, oh, this is an opportunity for the new infrastructure. Maybe building new road, building new transit route, and so on, to meet the high demands, to reduce the travel time. Negatively, we can also think that consistently high of the value of TC, that means inefficiency, because increased travel time, congestion on the alternative route. Okay, so it depends on short term or long term. Okay, so now when you practice that a while ago, you can also get alternative route and substitute route link. Okay, please check your work a while ago with this answer. Are they the same or not? Yeah. So use here we don't have alternative link flow, and here we also don't have. Okay. From here you can create the matrix. Yeah. So this is the indirect link flow. Okay. From the matrix set, you can create the count with this indirect flow matrix. And from there, you can also get the alternative route links and the substitute. Yeah. Okay. So, is there any question up to here? So, I give you the meanings. That means you can also do this. Yeah. So, in reality, things are not as simple as you think. Okay, so when I created this first time, so I created the algorithm, and it was my first algorithm or second algorithm, which is actually wrong. Yeah, so the correct one is actually this one. Okay? So I can prove that this is wrong by setting the counter example. Okay, so if you can prove certain algorithm, to prove the algorithm is wrong, is you just need one counter example. Okay? So in this example, yeah, the red one here, I can create very simple example here that actually we have this example that trajectory number 3 and 4 is actually incorrect. Okay, so and based on that, I corrected the algorithm. Okay. It is based on direct and indirect link flow. Yeah, initially I just used a set of union. Can you see this? Based on union of the set. That's why we have this indirect and indirect link flow. Actually, yeah. So this is the correct result. Okay. Based on the correct result, then you can get this. This is a very important example where the indirect link flow is exactly the same as substitute. Okay, when there is no alternative route. Okay. So if you look at this flow matrix, okay, and adjacency matrix, they are the same pattern, right? So when you see the pattern is the same in the same place when there is no for the to see the pattern, you can see the non-zero, yeah, the positive values. They are in the same place or not. Okay. Now in the OD matrix here, of course, you can see they are all filled up, including the to itself, right? Because there is a cycle here. Can you see this? There is a cycle from A to A. So here. Then indirect link flow, okay, is T minus F. So simply you get from these two, okay, T minus F, and then you can check, okay, that adjacency matrix multiplied by this OD matrix, you will get the F. Yeah. So why this example is important? This is to prove, yeah, that if you know the OD matrix, you can get the flow matrix. Okay? But if you know the flow matrix, there is no way you can get the OD matrix. Okay? It's one way. Okay? If you don't know the trajectories and you only know the flow matrix, you cannot get the OD matrix. That's the meaning of this lesson. Okay? This formula, the meaning is you can only get the flow from OD matrix. You can get the flow matrix, yeah? But from flow you cannot get back the OD matrix. So there is an information reduction here. Okay. So from there, okay, this is the relationship between network structure and network utilization. Yeah, you can practice this, okay, trajectories in the same network a while ago, and you can start to see, okay, that the direct link flow and alternative link flow, not the TC, but the T itself. When you add, then they are exactly the same as A times T. Okay, so this is very important formulas, okay, that we can use. Okay, so this is an example. So you have adjacency matrix a while ago. Okay, from there, from this trajectory, you can create the flow matrix and the OD matrix. Okay, and then you can also get the alternative route, right? And then you can test, okay, whether this relationship is true or not. Okay. Now, the next lab, okay, the next lab is about the relationship, yeah, between network structure and network utilization. So you can go to model Revoledo, okay, and go to the third lab here, the relationship between network structure and network utilization. Okay. So here it is, I open. So of course the instruction is almost the same. Okay, so you can create random network, okay, and then you can create random trajectory, okay, and you can also create your own trajectory by setting the node sequence, okay, and then you test whether the trajectory has full network utilization or not, okay, and then after that you can, there at the bottom, you can test the relationship, and additionally, okay, of course, you can test the network utilization matrix. So these are the example. You can set the network utilization matrix and test the relationship also. So I have preset a relationship that I want to test. Okay, so this is based on the relationship that we want. So if true or false depends on the thing that you put there. Okay, so this is the assignment that you will do in a couple of weeks. So do you want to test? So you copy and paste a while ago, the one that you have done in the network utilization, and put it here, the matrix. and the manual input of the trajectory. Okay. Do you want to practice this first? Okay, maybe a few minutes. Plan. Okay, so
Okay, sir. I did exactly what is in the instruction.
okay, so
So I confirmed that F plus T is equal to
it is correct. Okay, but
A
the others there are some
here.
faults. Right, right,
It's exactly equal.
exactly equal. Yeah, but there are certain
Yes.
relationship it is not equal. Yeah, so when they put false there, can you see up? Can you see up there? A
This one, sir.
is okay. So there are certain things that is not equal. There are certain things that equal. So you can start to see. Maybe you can investigate why. Right. So
So,
E,
sorry, sir.
you can
What was that?
investigate. You can investigate why they are.
Oh,
Okay.
okay.
E means and P is the part matrix. E is P minus A.
This one, sir.
Correct. So P E is basically the part matrix P minus A. Okay. So there are certain relationship that is still not correct. But anyway, with this, now I want you to practice. Okay. You have the tools anyway, so you can practice this. Go to the slide. Can you practice the waving section? And then you can also practice the general network. So 2%, okay, for practice. We have the tool that's not so long to create. And then check this, yeah. In the slide, there are two practice. One is waving section, and the other one is the general network. Both have 9 trajectories. Okay. Uh, when you recite, don't forget to claim your recitation. Okay. Okay. And put your total recitation on top so that I can just simply get that.
For the general
Oh, sure, of course.
network.
Yes, go.
Okay. The matrix is not showing because I have been disconnected earlier.
Okay.
But I inputted the 9 trajectories,
Okay.
then the 7x7 adjacency matrix. Then and the testing of the relationships F plus T and the Hardamat product of adjacency and order matrix is true. All are true except for this
These two.
the last four.
Okay. The last three is false.
Last, yes.
Okay. Okay, so f plus t equal at is true. All right. The second one is definition, so it must be true. Right.
Yeah.
The same thing with L equal to T plus S. This must be true because that definition. Yes. So, yeah, thank you, Vin. Very good. So, who else? Okay, Glenn.
Sir, I did the weaving section,
Okay, the waving
the
section.
first one. And when I tested the relationship, everything
True.
was true. Yes.
Okay.
And when I checked the output from this one to the one in the slides, on the slides,
Okay.
um,
They're also the same.
the results were also the same.
Yeah, very good. So, this is interesting because waving section, you know waving section, right? Waving section usually happen when there's a U-turn, okay, or there is a roundabout. So you have QC circle there, right? So that is the waving section. In any roundabout, okay, or a U-turn, okay, to calculate the flow there, okay, on the design in U-turn or roundabout, you need to compute the waving section. Okay, you need to know the flow in waving section. So that is part of this lesson. So and this waving section is also interesting. Why? Because there is no alternative, right? So T is 0 practically. Okay, so in that case, F equal to A times T, yeah, in Hadamard product. Okay. Thank you. Anyone else want to share? Oh, can you give me feedback? Is there any feedback about this lesson? So, okay, share with you the screen. So, last time we have this, okay? So this is a Hadamard product, yeah? This is not matrix multiplication, this is element-wise multiplication. So when you have adjacency matrix, multiply by the binaries flow, okay, you will get back the binaries flow, okay? You want to know whether the network is fully utilized or not, okay? Check the binarized flow matrix with the adjacency matrix. If they are the same, then this is fully utilized, yeah? If they are not the same, then this is underutilized. Right. So, and these are the relationship between flow set, this one with the tilde here mean flow set. Okay. So the flow set is always subset, yeah, of the OD set. Yeah. In that case, when you count, okay, because this is the flow set represent the number of the IDs of the trajectories. So then the flow matrix is always less than or equal to the OD. Yeah. So this is the count. This is the set. Okay. So now in terms of OD, okay. So when we binarize the OD, okay, they will be less than or equal than the binarized path matrix. So in fact, you can multiply the binarized path matrix, okay, in element wise with the OD matrix, then you can get exactly the OD matrix. Yeah? So this is called absorption rule. Yeah? So now when your network is acyclic, like the waving section a while ago, then you will have the F is equal to A times T. Yeah. So this is only happen in a cyclic network without alternative route. Yeah. So, but in general, we will say that F is actually less than T. Yeah. Remember that A times T is equal to absorption rule. So in that case, we can try to see another general network, regardless the network is utilized or not, that F is actually the same as A times F. Yeah, this is again absorption rule. So then if you binarize the path matrix, okay, the pattern will be exactly like the binarize of the T, the OT matrix. When you this is binarize the adjacency matrix, the pattern will be exactly the same as the pattern of the flow matrix. Yeah? Then the question is in that case, because external matrix is P minus A and L is D minus F, right? Then maybe the pattern should be the same, right? Okay, apparently, but this is not the case. Yeah. So in reality, the pattern of the indirect matrix is not the same as external matrix. Yeah? This is interesting. We define external matrix as E equal to P minus A. So in that case, the structure or the pattern, you can just binarize them, right? So based on the absorption rule, so we can, when you multiply element-wise, the binarized path matrix with the E, you will get back E. Okay, the same thing when the path matrix you multiply with the adjacency matrix, you get back the subset, yeah, the small one. Now, indirect flow matrix, in the matrix sets, you will get this. In that case, of course, the implication is that in the network utilization relation, you will have T is equal to F plus L. Yeah. So this become definition. Okay. Now, from there, we supposed to get this relationship. Yeah? The L is equal to binarize of the external matrix multiplied by T. Okay. This is only for a cyclic network. Yeah? For general network, they are not the same. Yeah? So a while ago, you can get the false instead of true. Okay. Same thing here. Now, with that, we can also compute the alternative route, okay, and substitute route here. Okay. Now, again, we can get the relationship between the network structure, yeah, A here is the network structure, and the network utilization. Yeah, T here is the alternative route, and L here is the indirect. Okay, with that we can also get other relationship. Yeah, in general network supposed to be supposed to be correct, but not sure why certain trajectory make it incorrect there a while ago, right? So this is the real part that we want to do now. So F plus T is equal to A times T. Okay. So in that case, because T plus TC is equal to L, okay, in that case, you can put that F plus T is equal to D minus TC. Right. So look at this. Look, you using matrix, okay, you can do algebra. Yeah, like as if a simple equation here. Okay, so this is the correct corresponding. Okay, so D origin matrix is correspond to the P. yeah, the p-binarized. Yeah? That means a path matrix that we binarize. Similarly, the flow pattern is the same as adjacency matrix, but the external matrix is actually the same as TC, yeah? not T, not L. Okay, so this is the summary, okay, of all this relationship a while ago. And now, because last meeting you presented your project, right? So I give you some ideas here. Yeah. So what can we do using this 4 or 5 matrices that we can use now? One is probably you can develop, crowdsource traffic information system. Okay. So when you, for example, you develop an app to collect user trajectories, okay, and then you can update this flow matrix in real time. Okay. With this, you can provide personalized route recommendation, for example. Okay. Another idea is to create automatic visualization from the traffic data. Yeah. So if you can visualize the direct flow, okay, and then with that you can identify the areas where the high alternative route, T, in that case, you can suggest there is a potential congestion or avoidant behavior. Okay. Then you can highlight segment of substitute flow where the new links or improvement need to be done there. Okay. Some of you doing bus, right? So in that case, you can also create, for example, a multi-modal system, yeah, based on bus, metro, or cycling, and MRT. So in that case, you can identify the key transfer point or the links where the indirect flow, T matrix is dominant. Yeah. So using intelligent transportation system, basically you can get trajectories, then you can enhance the coordination between different modes. Okay? So you can optimize the transfer time, provide real-time multimodal travel information. The same thing. So you can, based on the short-term forecasting, okay, you can observe whether actually F compared to the A times T. Okay, in that case, you can detect is there any anomaly. Yeah. So now, based on this model, okay, you can also do what is called AWS, yeah, early warning system. Okay? When there is a sudden change in the flow, yeah, or in the T, then you know there is potential incident or accident or roadblocks. So again, if this is connected to traffic signal, then you can provide alternative route, for example. Okay, so again, you can identify the bus route, for example, using direct link, which this part is actually underutilized, yeah? The flow that you can compare to A times T, and then you can redesign the bus route or the schedule. So these are several just ideas, yeah? So you can check whether this matches with you or not. Okay, so I just summarized all these lessons. Okay, so we are starting with static trajectory that can be obtained by a questionnaire or any tracking device. Okay, and then I showed the algorithm how we can get the flow, OD, desired line, and so on. Okay, and then using very simple linear algebra, okay, you can get the relationship between the network utilization and network structure. Okay, with that, you can start to do the assignment. This one, right? So you can create your own network, okay, with at least 4 nodes, maybe 7 links, and you can create your own trajectories and then try to compute in spreadsheet probably to get these values. And then you can compare using the tools available. Okay. So yeah, you can also use this in the virtual lab a while ago. So, any question about this topic? Yes. why there are repeated trajectories in the waving section? Okay. In the waving section, okay, you have only 4 possible path, isn't it? So in that case, if you want to create more trajectories, then you can repeat the trajectories. So repeating trajectories is fine. Of course, if the same agent can pass to the same route, okay, or different agent also can pass the same route, isn't it? So repeating trajectory is okay. In fact, I think in 2014, I got a project from DOST. So to create this, using mobile device, we can track the people, and then do update in real time. Any other question? So if not, shall I close this topic and we go to the next topic? Okay. Okay. So let's go to the next topic. You go to model. Okay. The next topic is about transport demand analysis. Okay. A while ago, we talked about network structure, network utilization. Network structure represent the supply. Network utilization represent the demand. Okay. So there is a traditional method to do this transport demand analysis. Okay. Which called traditional transport planning. Okay. So go to that slide. One. Can you see?
Yes, sir.
Okay, good. Let's start. Yeah, this is traditional, okay, the old model. Okay, so still classical, maybe. These are the topics that we will discuss in this slide. Okay, so what's the difference between forecasting and planning? Okay, and urban transportation planning process. Okay, and then we start with simple forecasting. This include factor, simple linear regression, non-linear regression, multiple linear regression. Yeah? And again, we will discuss the scenarios info eventually. Okay, start. So what's the difference between forecasting and planning? Okay. So when we say both forecasting and planning, okay, both are about prediction, okay, prediction about the future. Okay. So you are the modern wizard, isn't it? So in the past, wizard supposed to predict something, yeah. So or prophet, okay. So we based on science, okay. So in any prediction, okay, we base it on the previous data, okay, and in any prediction, we always have certain assumption, and there is certain invariant. Invariance means something that don't change. Okay, there is something that we assume that they don't change. Okay, without these two, we cannot predict. Okay, so what's the difference between forecasting and planning? Okay, forecasting is passive, objective. So we predict what will happen in the future without our intervention. Okay? There is no control. There is only forecast, prediction. Okay? So planning, okay, use forecasting, yeah? Objective forecasting. But the difference is planning is actually active. and subjective. Okay, so we control what will happen in the future. Okay, so first we forecast what will happen, and then we control, yeah, based on what we want. So there's a goal. Okay, so planning is level 3. Yeah? Level 3. Yeah? Forecasting is level 2. Level 2. So what is level 1? Level 1 is understanding the problems. Okay, so you want to control, you want to guide what will happen in the future based on certain action that you want to control the path. Okay? In that case, planning should have certain goal, certain objective. Okay, so here is the goal of urban transport planning. Yeah. Very long here. So planning basically a process to examine the potential future action, okay, to guide the system toward our desired direction. So this is in general, right? But for urban transport planning, it's the same thing. It's a process. Okay? You want to prepare the physical facilities and services, okay, of all mode of future transport, not just currently. In the future transport needs in the urban area, because this is urban transport, yeah, in order to provide, these are the goals, yeah, to provide safe, rapid, comfortable, convenient, economical, environmentally compatible, and efficient access. And of course, the mobility, yeah, for the people and goods. Yeah, the basic idea is to satisfy human needs and activities. Yeah. Transportation is derived demands of activities. Don't forget that. Okay, so when we say about transportation planning, it is actually multidisciplinary. Yeah? It will combine social science, economic, maybe you have background from architecture or system engineering, or some of you from civil engineering. Okay, you can also come from various background in mathematics and statistics and so on. So these are the various multidiscipline aspects, yeah, of transportation planning. So when you go to the physical science, okay, here is the boundary. Okay, there is an overlapping between transport planning and traffic engineering. Okay. When we talk about transportation engineering, we'll cover everything here, yeah? Transport planning, engineering, kinetic design, and soil pavement design. So our part is in here, yeah, transport planning. So not geometric design, not traffic engineering, not pavement. Okay, so now these are the UTP, urban transportation planning process. So again, you start with the goal, with the objective. Okay, and then what is the organizational goal? Okay, what is the policy and technical things that you have? Okay, then you want to get people to participate, yeah, citizen participation. So when you have a project, okay, after you create a plan, okay, you need to inform the public and get the feedback from the public. Okay? So, example, some part of my project in 1990s, yeah. So we try to relocate the market, okay, and then clean up the market to become a road, for example, was I propose already that we have citizen participation, but apparently the government officer at that time did not want to do it, probably because of the budget, okay, and eventually failed. Yeah, the project failed because once we start the project, okay, the public opposed this, okay? And so this is clearly waste of time and money if you don't do citizen participation. Okay, then to do the urban transport planning, you need to collect the data. These are the usually the data that you want to do. Yeah. So population data, economic activities, land use. Yeah. What is the current transportation system and what is the travel behavior? Okay? How the facilities in the terminal and how the transfer. Okay? What is the regulation and traffic control, including the finance and the values. Yeah. This is also very important to deal with the culture. Yeah. And check whether this plan need immediate or a long term. Okay. Then in terms of analysis, the one that we discussed in the class is this part. Nah? So basically just this part with this trip generation, the distribution, modal split, and profit assignment. Okay. Based on that, okay, we forecast. Yeah? Based on the data that you have, you forecast the population, land use, economic, and so on. Okay. And connected to this model, then you can create an alternative system. Yeah. Again, in the future, okay, what will be happen? Because you already forecast, then you apply the same model. Okay, okay? And then create a plan for implementation. Okay, and we suppose to have a feedback system. Yeah? That means you do appraisal and surveillance after you, whether the planning is actually the same as what you, the implementation and the behavior is actually the same as the plan or not. So this is also very important. And feedback system is very important. It's often neglected by the government and consultant here. Yeah. So whether our goal and objective is achieved or not. So this is the main point of UTP process. Of course, the main core is in this 4-step models. Yeah. So we have trip gen, trip distribution, modal split, and traffic assignment that we will discuss maybe from next meeting. Yeah. So what is this in big picture? Yeah. So in the big picture, trip generation is basically we want to know, okay, the decision of each individual to travel given the trip purpose. Okay. In the second step, so we call it 4-step model: trip gen, trip distribution, modal split, and network assignment. In the second step, okay, trip distribution, we want to know, okay, what is the origin and destination. So again, this is the input, yeah, of the whole model. Okay. The third one is actually mode choice. Okay. How they use mode, whether they use bus, they use car, or use MRT, jeepney, and so on. Okay. And all of these three will be inputted to the last one, yeah, traffic assignment or network assignment, which route, or which part they are using. Okay, the final goal is basically you get the flow matrix. Yeah, so this is the classical technique. Yeah, so in here, in the first step, you have the economic activity and population and land use. Okay, so and then you create the OD matrix, and then you separate them into which mode, okay? And then here which part. Okay. So here is the purpose of travel demand model, and basically you want to predict the future traffic volume flow, okay, from the origin to destination by certain user groups. Okay. Usually the group based on socioeconomic income. And then for certain trip purpose, okay, using a certain mode at certain route and at certain year, yeah, in the future. Okay, so these are the main transport demand model. Okay, so up to here, is there any question or discussion? you know very clear the difference between forecasting and planning. Okay? So, and you also know the purpose, goal of this. Big picture. Now, still in big picture. Is there any question? Okay, so if not, okay, I will go to the next topic. So, which is basic forecasting. Yeah. Okay, with some numerical examples. So, one simplified approach of this is we want to know the transport demand and transport supply. Right? So in that case, you need to know the population, okay, land use, and economic. Okay. After that, the whole region you divide into zone. Okay. In the simplified process, you divide into zone. Okay. After that, you compute and you forecast, and you calibrate the model, and then you forecast. Okay. And check what will be the future level. Okay. And then you create also the alternative. What will be the specification of the change of network structure, basically? Yeah. What will be the change? And from this alternative, you compute the cost and then check whether this is good or not. Yeah, we compare, we evaluate each of these alternative scenario, and then put this as our project selection. Okay, so these are the simplified UTP process. Okay. Now, for forecasting, okay, the very simple model is called growth factor. Okay, growth factor, say, for example, yeah, you have P is the price or population or economic GDP and so on. So it depends on you who define this. So say example price, okay, or population. When we put the subscript T minus 1 here, that means yesterday or last year. Okay? And we put T here, subscript T here, that means today or this year. Okay? When you put T plus 1, that means tomorrow or next year. Okay, so the formula is rather simple. Okay, so we call this return. Okay, return at time T today, okay, is the same as the price today minus the price yesterday divided by the price yesterday. The same return of today is population this year minus population last year divided by population last year. Okay, so in that case, we can you can, if this is T, you can also look at this because this is T, so you can add plus 1 here, right? So you can plus 1 here. That means everything now become plus 1. Yeah, this one also plus 1. Yeah, this one also plus 1. Okay, but minus 1 plus 1 is 0. So now this one becomes PT. Yeah? So yeah, so we can have also PT because we add plus 1 in everything. Okay, now this is the assumption now. Yeah, in growth factor, okay, the assumption is the growth did not change. Yeah, so this is the invariance. Okay, so when the growth did not change, okay, then PT plus 1 minus PT is basically divided by PT is the same as tomorrow compared to today is the same as today compared to yesterday. Okay, so now with this, okay, using this formula, you can easily get the PT plus 1, right? You can see this. And because they are the same, so you can get from here now you can get the PT plus 1 is equal to RT times PT, isn't it? Yeah, multiply this, right? So, and then this part you can go here, so plus. So now this one we can simplify, equal to PT plus 1 plus the growth factor. So this is the actual formula that we use. Okay. So, can you compute, okay, the growth factor for this population in 2025? Is it possible? So, if this is the population that you have in the past 5 years, what will be the population next year? So, okay, first you compute the growth factor, okay, and then you forecast. Yeah. This is the formula. Okay. To forecast, remember, to forecast, you need to assume. Yeah, you need to assume invariance. Okay. So then you can get this. Okay, so you want to try this first? And after you try, maybe you can have some feedback. Okay, so you get the same answer. Easy, eh? Yeah. Now, so here is the main part. Okay. Can you see the slide? This. So these are the level, 3 level a while ago. Yeah. So this is L1, yeah. This is L2, and this is L3. Yeah. So when you do modeling, okay, you transfer. Right? So level 1 is to understand the phenomena, yeah, or behavior. Okay. Observation. Through observation, you collect data. Okay. Then you get what is the best model that fit your data. Okay. And then which variable to be included and based on your survey and what are the coefficient values. So if I put it this way, yeah, this is your output Y, yeah, and this is your input X, right? And then how to calculate this? Okay, so this is your output, right? And your input is X, yeah, your output is Y. And then what is the best model? So let's call your model is F function. Okay. And what are the variables to be included? Of course, the input and output. Okay, many input and probably one output. And what is the value of the coefficient? Okay, let's call this coefficient alpha. Okay. So level 1 is to understand, okay, your own data. Okay. So, and then from there, you can try what model will be the best fit, yeah, for this. So you have the input, you have the output, you have the model, and you have the parameter, yeah, the value of the coefficient alpha. That is what we have. Okay. So basically, you will have something like this. Now, Y is equal to function, right, of X, comma, alpha. Yeah. Okay. So understanding phenomena is important. This is the first step, okay, but not enough. Okay. Many people in different field, you ask them, oh, do you understand this? Yes, they understand very well. Okay. Can you predict? No. Then they are in level 1. Okay. So level 2, okay, given the same y equal to function of x and alpha. Now, what is given? You have the input x, yeah? You have the model f, okay, and in level 1 you calibrate this, right, the alpha, okay, and you assume, okay, this is the important part, yeah? The assumption is your f, your model, and your alpha does not change. Remember, the invariance is very important because any model, if you don't know this assumption, then your model is useless practically. Okay. So you need to know the assumption. Okay. So the assumption is, okay, your function, your model does not change. Your calibrated parameter does not change. Okay. Then you want to get what is, if I know the input x, okay, then what will be the output y? Do you understand? Now, in planning, it's not enough just to forecast. Okay? You need to control, right? You want to intervene, right? So to control, you need to have goal. Okay, you have target, you have the objective. So that goal represents the output. So you have the goal, the output. Okay, you have also the model F. Okay, the one that invariant is actually the F minus 1 and alpha. So these two are invariants. This is the assumption. Okay, you have the output, the goal, you have the model and calibrated in level 1 go. Now you want to get what is the input that I need to change in order to get that goal. Do you understand? Yeah, in an abstract term, okay, if you want to do planning, basically you need to go to level 3, okay, of modeling. It's not enough just to forecast. You need to be able to optimize, to control. So what is control? Knowing the goal, the output, okay, and knowing the model and the parameter, you want to know what input should I change in order to get that goal. Is it clear or not? Okay, so let's try, okay, next simple techniques called regression. Okay, in regression is a modeling technique of numerical data. Okay. So you have input of what do you call that? Okay, input of x, yeah, many input x 1 and 2 p, and you have one variable, okay, output y. Okay, so the output variables is called dependent, okay, because they are depend on the input. And then you have one or many, yeah, independent variables. So these are the input. So basically, okay, your model represents a system. Okay? A system should have an input and an output, isn't it? Okay, so the input is x, the output is Y, say your system name is E, yeah? Dot here represent the input. So then you will get Y is a function or function of E of the input, yeah? So when we said function, system, model, they are actually equivalent, okay? So now when we said a linear system, so a linear system, okay? So yeah, a system is called linear, okay, when these two conditions is satisfied. Okay? Number one, what? Okay, the system that receives the sum of two input. So you have x1 and x2. Okay? It will produce output equal to the sum. Okay? So remember E a while ago, if you have x and then the system is E dot, then output is exact, right? So then if this system is linear, okay, criteria number one is when the input are added, okay, then this output can be separated. Can you see this? The output can be separated, yeah, as addition also. Next criteria, if the input is scale, multiplied by certain constant, okay, then the output will have exactly the same scale. Okay, so this is by definition, this is what is called linear system. Okay, so then we can combine the two conditions above, okay, into one. Okay? So what if I just add and then multiply together? So we have like this. Okay? Then of course you will have, okay, you can add the output and you can put it out the scale factor. Yeah. So this is the definition of linear system. Is that okay? Is there any confusing part here? Linear system. Yeah, usually the graph is straight line. Okay. So this is example of linear system. Yeah. So when we say linear regression, okay, they are linear in parameter, not necessarily in variables. Can you see this? Look like this is non-linear because they have this square and exponent p and so on, but they are still linear because, okay, by definition, okay, linear system is you can put it out. You can add and you can put it out. Is this clear or not? Okay, so there are certain example here. Okay, so which of this example is actually linear or no, which one is non-linear? Oh, anyone? How about this one? This is linear or non-linear?
Linear, sir.
Oh, this is linear. How about this one? Linear or non-linear?
Non-linear, sir.
Oh, non-linear. Can we transform this to linear? How about this one? Non-linear, right? Can we transform this to linear? Yeah. In fact, all this model, okay, uh, so look like non-linear, okay, except this one is clearly linear, yeah, but they can be transformed, yeah, into linear. So all of these models are linear models. Okay, so later we can discuss how we can transform that. Okay, so let's start with the simplest one. This one, yeah, y equal mx plus c. Is that okay? Okay, so y equal to m x plus c, isn't it? Yeah. Y equal m multiply x plus c. Yeah. So the m here is the slope, c in here is the intercept, isn't it? So it's basically a straight line. Okay. And be careful, the error is measured this way. Yeah. So, okay, let's try this. So I have a data from 1980 to 2000. Can we compute the, oh, actually this is the same data as a while ago, right? In the crude method a while ago. So just different year. Okay? So can we compute this using regression? Okay. So let's try, yeah. So when we do regression, so we have 5 data points. Okay. Can you plot this data? Okay. Let me open Excel. Yes. Yes, yes. Yes. Linear, non-linear. Okay, good. So if you input this in Excel, so I will demonstrate to you. Okay. Can you also do the regression of this? So what I will do is to type this data. So let me share the Excel. So I create a new sheet, right? What's the data? So let's start this data here. I have 2.1, right? And then 2.9, right? And then 3.2, and then 4.1 and 4.9. So let's put the year here. And this is the population. Yeah? Population. Okay. The year we start with 1980. So this one is an additional every 5 years. Right? So this one we don't know. You want to know this one. So first thing first, yeah, when you have this kind of data, what you will do, you highlight and then go inside and plot, right? So we plot this. Yeah? Okay. Can you see? Okay, so it's look like a straight line, isn't it? Oh, so it look like a straight line like this. So what will be the regression of this? Okay? So can you plot first? Yes, Glenn.
Sorry, sir. I can't seem to, I don't see your presentation.
Oh,
The Excel file.
You cannot see that actually. I'm sorry. Okay. I think I shared it. Let me see. Hmm. Okay. Oh, okay. You can. The Excel file is not showing. Well, let me share the whole screen. Can you see?
Sir, can I share?
Yes, sir.
Yes.
Okay.
Okay. So yes, please. You want to share? You can share.
I just want to check if it's correct, sir.
Hmm. Cool. Yes, Vincent has already did the population. I cannot see yet your screen, Jochen.
I think, sir, it's lagging.
Oh, okay.
But I just did, sir, plot the points,
Okay.
then scatter plot, then
Okay.
show trend line.
Okay. Great. Okay. Okay. So you can you already know how to show trend line. That's super. Yeah. So
And the equation, sir.
that's the regression. Very good.
Yes, sir.
So now I want to ask. Okay. So let me open my. Can I share? Is it okay?
Yes, sir, you may. I will just.
Okay.
It's lagging, sir.
Yeah. So let's go to the second screen and show this. Okay. So what happened is when we plot this data, okay, we get this, right? Okay. So we said, oh, it seems the model should be straight line, probably is the best. No? So, but the question is, which is the best line? The red one, the blue one, or the green one? Yeah. What do you think? Yeah. Yes, the green one. Is it? Why? Why the green one, Vin Sanchez? Huh? Is the average? Oh, okay. Mark said the red one, so everyone have different opinion. Who said the blue one? Okay, so this one said the blue one, the other one said the green one, the other one said the red one. Yeah, so everyone will have the red one. Yeah, okay. So many of you said the red one. Probably correct. Yeah. So now look at it this way. Okay. That's red is overfit. Okay. So what is actually the best model? Okay. So that's the best model depends on the criteria. Okay. What is best? Right. So then we can start to argue what is the criteria. Okay, so the blue line passed through the first point. So this argument, the green line is in the middle. Okay, one said you said the average. Okay, and the red one probably passed the most data point. So these are the argument that you can always say. Yeah, but there are some objective criteria that we use. Okay? So one criterion is actually error. Okay, so error is discrepancy between the model that you predict and the real data point. Okay, the question is how do we measure the error? Okay, so when we measure it this way, error is positive when the data point is above the line and negative when the data point is below. Yeah. So when you measure it this way, then you will get least square. Yeah. So we call it least square because you want to minimize the sum square of error. Yeah. So internally, you are actually assuming that this is normal distributed with zero mean and constant variance. Okay. So when you try to calculate the sum of error, it will not work because the sum of error will always become zero. Okay, so that's why you need to square the error so that it will not become zero. Okay, so let's compare the blue and the red and the green one. Okay, so I just plot it manually and then approximate manually here. And these are the data, right? And then we get the value and then we calculate the error. Error is just this value with minus this one. Okay, and then we square it. Okay, and oh, the red one. Okay, get the minimum among the three, right? So then the question is, can we obtain the best line model without guessing it? Yeah. So this is actually the formula. Yeah. So this formula you can derive on your own based on the model. Okay. And then you can take the first derivative and then equate it to zero. Yeah. Then you can get this value. Yeah. This formula. So what is the meaning of this formula? Okay, n represent the number of data. Okay, and x, of course, the x available, the year. The y is the output. So in this case, the population. Yeah. So sigma here is the sum. Okay, so in here you sum the you multiply first x and y, and then you sum. In here, okay, for each x you sum. So here, the y you sum. Here you square first and then you sum. Okay. Here you sum first and then you square. Okay. And then you take the average. Okay. You get the flow by computing all of this, and then you multiply with the average of the x. Then you can get the intercept. Okay. So if in this example, okay, if you want to do it manually, okay, without Excel formula, this is what you need to do. Okay, so you get the x, the year, and the the y, the population, okay, and then you take the sum, right? Sum of all of this is 9,950, and then you take the average. Yeah, so these two columns you can get the sum and the average. Okay. After that, what you will do, you multiply 1980 multiplied by 2.1, so you get 4158. Okay. Then you multiply x with y. After that, you square the x. So 1980 squared, so you get this. Okay. And again, you get the sum here. Okay. Once you have this, you can calculate the slope. Yeah. N is, of course, the number of data. So 1, 2, 3, 4, 5, n is 5. Okay. sum of xy, that means this is the xy, right? So this is the sum. So 3, 4, 2, yeah, 6, 2. And then the sum of x, that means this is the x. The sum here, this is the sum. So you put it here. Okay. The same thing, the sum of y, you put it here, 17.2. Yeah. And then what is this? This is you square first and then you sum. So this is the value. Okay. And this one is you sum first and then you square. So this is the sum and then you square. Yeah. If you multiply and you compute this, you will get exactly the same like what you did there a while ago. Yeah. After that, you get the average here. Okay. And then this is the slope, right? And you can get the actual value. So then the model is as simple as this. Yeah? So population is the slope multiplied by the year and with the intercept. Yeah. So this is the model that you have. Okay. Now understanding the model, this is level 1. Right. Now go to level 2. What? So to predict. Right? So in that case, if you know the year, because the input is year, so if you know the year, then you can predict the population. Yeah, simply inputting 2005 and 2010 in the year here, you will get this value. Right? So up to here, is there any question and feedback? So if you have the Excel, okay, you can go to the trend line. Let me show next. Are you? No. So let me open the Excel. Okay. Yeah. Many of you already know how to do regression. So one way is to compute. Okay. So you need to compute the slope, right? And the intercept, isn't it? So in that case, you just equal. Can you see? Equal slope. Yeah. The slope, what you see here, the known y and the known x. So what you know is this is the y, and then comma the known x. So there you get 0.36. The intercept equal intercept. Intercept there. Yeah, again the same known y and then known x. Right? Then you can get that value. Yeah. So another technique is to use this. Okay, and right click. You will see the trend line. Okay, and say the linear here. Okay, and you can display the equation and put the R square there. Okay, and Excel have several nonlinear model that you can also use: logarithmic, polynomial, power, and moving average, and exponential. So these are basically only 4: exponential, logarithmic, and power. Because polynomial and moving average are interpolation rather than extrapolation. Yeah, it will become overfit. Okay. So up to here, is there any question? So you can also use, okay, in Excel, there is also data analysis. Yeah. So let's see if we can use data analysis. So go to the option, add-ins. go here. You click the analysis toolbar here. Okay. Then, if you have analysis toolbar, you will see here data analysis. Can you see? Data analysis. Okay, and then you can do regression. Okay, regression. A lot of analysis here. You can do ANOVA, correlation, and so on. So you just choose regression here. Okay, and the input range is Y, range is this one. Okay. I will include the population. The X is the year, right? Okay. And because in the beginning I put year and population, the label is there. Okay. This is interesting in data analysis. You can put the residual, standard residual plot, and fit, normal distribution, and confidence interval, and then click OK. Yeah. So it will compute. Can you see? Okay. So this is the result. So many numbers here. Okay. Three things that you need to get. Yeah. Number one is the coefficient. Yeah. These are the one that you need to get. Okay. Which is exactly like a while ago, 0.36 and negative 267.2, right? Exactly. That number, yeah. So then you need to check this one, T statistic, yeah. This T statistic you check, okay. They must be, absolute value of this T statistic must be larger than 1.9. Yeah, this must be the absolute value, yeah, the T absolute, so I'll put that this. T absolute, yeah, must be larger than 1.66. Yeah, this is based on normal distribution. Yeah, and then this one, significant F, must be less than 5%. Yeah, it must be less than 0.05. Yeah, so this is the check, and then the R square, yeah, or adjusted R square. Yeah, okay. This one must be larger than 0.8. So, oh, they are passed all correctly. Yeah, so this is good. And the nice thing here is you can start to see the probability plot and residual. Okay, if they are correct, the residual will represent whether the error is actually there is no pattern in the error. Yeah, and this is the fitness of this predicted and the actual value, they are almost correct. Okay. The same thing, whether the normal probability plot, we'll see whether they are actually normally distributed or not. Yeah, because this is the basic assumption. Okay, this is the plot of these values. So up to here, is there any question? So simple linear regression, I guess you can do easily. Using the same data, you can predict. Right. So actually, modeling itself is an art. Right? Now, you need to guess. Yeah. Okay. It's an art because you don't really know which model will be the best model. So it's not necessarily linear. Yeah. One of them is linear. So first, what you need to do is to do the scatter plot, yeah, whether and then check the fitness. Yeah. Another way is to use the goodness of fitness, goodness of fit. Yeah. For example, the R square, the F test a while ago. Okay. So, okay. The formula that we passed a while ago is based on what is called OLS, ordinary least square. Okay. So in this case, you get the difference between the estimate, okay, of the output dependent variable and the estimate. Yeah? And then you square it. These are representing the error. Yeah? Error square, and then you sum. So this is called sum square of error. Right? Now, if you know the sum square of error, you take the first derivative of this with respect to its parameter. Yeah? Then, for example, our model is like this. Okay, then you can do OLS by setting the first derivative to 0, and then you can get different formula, yeah, compared to a while ago. Okay, so do you want to practice this or a while ago? If you have a straight 4 points, and if you plot they are close to the straight line, can you find the regression of this? Yeah. So you can compute by hand only 4 points. Okay. Then you can get this slope and intercept. Or you can use the Excel function or trend line or data analysis. Yeah. So you want to practice or you can complete? What do you think? Okay, you practice first. Now, if you have population data or economic data, yeah, then you can also plot, and then you can also regress to regression. To know the future, you need to regress. So in regression, for population and economic, usually the independent variables, okay, one of the independent variables usually time.
Can I try, sir?
Go.
I hope it will not be laggy again.
Okay.
Can you see now my screen, sir?
Let me see. Can anyone see Joven's screen? Oh yeah, I can see. Okay. Good. Now you have
I did both methods, sir. The hard calculations, then the plotting.
super. Okay, so 2.4 and 9.2. Yeah. Okay, good.
Yes, sir.
Very good.
So I get
Yeah.
both shown. Here's the
Okay.
equation and plotted,
Correct. Correct.
but it has a low value of R.
Hey, the R?
R squared, sir. R squared.
Yeah, it's 0.7. Is that? Yeah. Well, for certain data, if you have of course, if only little data like this, so you probably want to get different model, yeah, not linear in this case. Yeah, because the value of R square is low, so you probably want to try different model. Okay.
Yes, sir.
Okay, so thank you, Joven. Let's go to the goodness of fit first. Share screen. My screen. Okay, so the three things that you can measure. Okay, the most important goodness of fit measure are R square and T statistic. Yeah. R square is useful for the whole model. Yeah. This is usually similar to F statistic and standard error. Okay. And for T statistic, usually for each individual parameter. Okay, so this is the rule of thumb to fit for the linear model. So R square must be larger than 0.8 and the T must be larger than 1.96. Yeah. But just fitting the value is not okay if you don't have actual causal relationship. Yeah. So the model must have causal relationship to be interpreted correctly. Okay, and very important is actually to check the sign of each parameter. Yeah, the sign of each parameter must be correct. Okay, so you can test, okay, overall fitness using R square or using F, okay, to compare several models, which one is the best, and then you get the best model which is correctly fit the variation of the data. While the t-test is useful, okay, if you have many variables and then you want to remove some redundant variable or you want to remove some weak variable, that probably weak means they exist by chance. Okay, so the number of 1.96 a while ago is basically 5% error. Yeah? But they are actually just because of chance happen there. So the formula of R square is basically 1 minus SSE divided by SST. What is that? Okay, SSE is the sum square of error a while ago. The error is the observation minus the estimate. Okay, and then you square it and then you sum. So this is SSE. So SST is the sum square of total. What is this? Sum square of total is the observation minus with the Y average. So you get the average of the output, okay, and then each observation you minus with the average, and then you square it, and then you sum. So this is called total variation. Yeah. So when we have 1 minus SST divided by SST, then you get R squared. Why this is important? Yeah, even in later in IFN or in other model, we can also use this. Yeah, this the same formula. Okay, even a nonlinear model, we can also use the same formula. Yeah. So in this example a while ago, so I can compute the sum square of error. Yeah, this is the Y. Yeah, yeah, this is the YI is this one, the YI. Okay, and then the Y, oh, the Y caret here is the predicted. Oh, I did not put it here. And then we just need to compute this minus the error and then you square it. Yeah? And then you can just get the sum. And 0.88 and this one is the observation minus the average. This is the average is this one 3.44. So each observation, so 2.1 minus 3.44, and then you square, you get this one 1.8. And then you get all, and then you sum, you get this value. And the R square is this one, yeah, 0.88 divided by 4.1, and then 1 minus of this. Then you get this value. Okay. But if your model is actually multiple linear regression, that means you have more variables than just one. Okay. R square alone is not enough. Okay. Why? Because you have many variables and you have many data. In that case, you're supposed to use adjusted R square. Yeah. What's the difference? In R square, you use S, sum, SSE, SST, right? So in adjusted R square, you don't use the sum, but you get the mean. Yeah? So the computed mean square of error is based on SSE divided by the number of data minus the number of variables. Yeah, Q, and this one is of course this is based on the data, so n minus 1. Okay, and For the rule of thumb, okay, if the R square or the adjusted R square is higher than 0.8, then this is good linear model, right? But if this is less than 0.5, then you probably want to use other model, yeah, maybe non-linear. Okay, and of course we can also compute the standard error. Data analysis in Excel produce this value, so this is just the formula to get that. Okay, and the F statistic is based on this formula, okay, a while ago to get the table, right? So the one that you use data analysis, you will get the ANOVA table, yeah, with the F statistics. This is the one that you will compare with 0.05, yeah. Again, F statistic is to check the overall fitness of the model, yeah. While the T statistic is for its variables or its parameter. This again, I just give you the formula so that you can, if you want, you can compute by yourself. Yeah? So these are the summary. So if you have alpha 0.05, that means 5% error. So you can use this. If you have 10% error, you can use this value. Yeah. So these are the three simplified technique, yeah, to check whether your model is good or not. Okay, a while ago we have from data analysis in Excel, you get this value. So these are the things that we need to get. Okay, okay. With this, we can use Excel function, data analysis, graph, and you can manually compute. Okay, the one that we did not use is actually the matrix. Yes, you can also use matrix. Yeah. So later. Now let's discuss certain nonlinear regression. Yeah? So when you plot the data into scatter plot, okay, and when you see they are not straight line, that means probably this is nonlinear. Then you can guess. Okay, you can guess what is the nonlinear model. Okay, and then you transform that nonlinear model into linear. Yeah? You try, if it is possible, you transform that nonlinear model into linear, and then you can compute the model parameter, and then do all the same thing as a linear model. Okay. So again, here is the example when you do the scatter plot. Okay, and you will have the trend line. Okay, and then you can start to see here if the curve is something like this, logarithmic. Okay? If like this, then this is logarithmic. If the curve is something like this, then this is probably on polynomial. If the curve is something like this, then this is probably a power or exponential. Yeah. If something else, then probably you can use moving average. Okay. Excel only produce this a few models. Okay, but you can generalize later. Okay. So with that, you can be careful. Yeah. So if your data, if you are using polynomial, say for example degree 6 here, they will become overfit. Yeah. Overfit means it will fit with the data. Okay, very good. Maybe R square is very close to 1. Okay, but okay, it cannot be extended. Yeah, extrapolation is not good. Okay. So now, if you have some nonlinear model, something like this, okay, or something like this, you can actually transform into linear model. Okay, so this one you can take logarithm in both sides. Okay. Okay. In here you can take logarithm again, and then you will get linear model. Okay. In here you can just take 1 over, then you can get a linear model. Okay. So to do that, okay, let's review certain basic. This is probably you learned this in high school. Okay. This is the basic of power rule. Okay? Okay, so if you have positive A and B and any P and Q, okay, so E here is an exponent or Euler number, 2.7172. Okay? This is a constant. Okay, so if you have a E exponent of P multiplied by exponent of Q, then the exponent you can add. Yeah? The same thing, if you have a exponent of P and then you divide, okay, with exponent of Q, then the exponent you can minus. Yeah? But the exponent of exponent you can multiply. Yeah? And then if the exponent you divide, okay, that the same as you take the square root. Okay. Now, if you have a logarithm, okay, if you have logarithm of E exponent P multiplied by E exponent Q, something like this, then ln of this, you can put only the exponent, you can put it out. Yeah, ln of E is 1. Okay, the same thing, ln of P multiplied by Q is actually this one. Yeah? P multiplied by Q itself, because ln of E is 1. Okay, now if you have ln of E exponent P divided by ln of E exponent Q, then you can, based on this one, okay, then you can, ln of E is 1, then you can put it out. Okay, the same thing, because ln of E is 1, then you can have a direct division. Okay, now because of this, okay, now this is the definition of E. Ln of P is actually equal to P. Yeah. So if you multiply Q and E exponent P, then you can put it inside. Yeah. The Q you can put it as ln Q when you put it up there. Okay, this is the basic our rules that you learn in high school. Okay, I hope you remember. This is just a review, and I hope you also remember logarithm rule. Okay, if you have a log of x plus log of y, then you can multiply. Yeah, if you have log of x and minus log y, then you can divide. Yeah, and if you have a square root, that is the same as 1 over p multiplied by log x. Okay? If you have x exponent p, then the p can go down, so become multiplication. Yeah, from product you can make it into exponent, from the root you can make it into inverse, and so on. Yeah, from minus you can make it into division, and from the sum you can make it into product. Okay, now with this you can transform. Okay, sum of nonlinear model we can transform into linear model. Yeah? So in this case, the R square, the T statistic will not change prior to transformation. Okay, with this is the example of table of linear transformation. If you forget, okay, you come back here. And this is the summary that I have derived. Okay. So let's go one by one so that you get better understanding of this. Yeah. Say we use the first one, okay, A x exponent b. This is our model. Okay. So our model is y equal a x exponent b. Okay. Then what you will do? Okay. Then you will log. Yeah. You will take the log, right? Log of y. Log of y. So let me put it here. Log or ln of y, yeah, equal to what? Ln of a plus multiply by x exponent b, isn't it? So because you ln on the left hand side, you can take the ln of the right hand side also, right? So then this right hand side is the same as what? Ln a multiply by a of b, then is equal to ln a, right? Plus b ln x, isn't it? Yeah. So this is still the same. So ln y. Okay. Then I can substitute this one. Yeah. The ln y, I can put this as capital Y equal, what is this? Ln a. Ln a, I can put this as alpha plus b, I can put it as beta. And ln x, I can put it as capital X. Oh, I got a linear model. Yeah. Okay. By taking logarithmic to both sides, okay, I can get a linear model where, yeah, alpha equal to ln A, right? And beta equal to B. Yeah. And be careful, X, yeah, now become capital X here, ln X, yeah? And then ln Y become capital Y here. Okay, so come back to this table. You see, so this is the transformation that you need. Okay, this is after the transformation you need to return back this value. Okay, so let's take example. So let's take example of this data. Yeah, you practice, yeah, this data. So you type this data in Excel, okay, and then we try this. Yeah? So what you will do? Because we put it as linear model like this, right? So capital, okay. So that means the data. This is the data, right? You need to transform this data, okay, into new data, which is capital Y is actually log Y. This one. A capital X is actually, yeah, this is capital X, is actually log X. Okay. So then the one that you get the slope and intercept is actually from this one, yeah, from log X and log Y. Okay. So when you get the slope and intercept, you will get this one. This is the intercept, this is the slope. Okay. And then what you will do, because you already get the slope and intercept, you need to return back to the original model, yeah, which is A and B, not alpha and beta, right? But beta is equal to B, so in that case, no problem. But alpha, yeah, in here I put log 10, so in this case I will put 10 exponent alpha, so I get this value. Okay, so is there any question up to here? If not, okay, can you practice, okay, this one, yeah, 1, 2, 3, 4, 5, 6, 7, 8. So we have how many people here? Um, 12 person. So okay, you count now. You have how many? 8 models. Okay, count 1 to 8, and then next one is also 1 to 4. So who will be? Okay, you count. I will assign you the model, and then you will do that using this data. Is that okay? Okay, Adrian number 1, Albi number 2, number 3, glycerin, say 0, number 4, Glenn, number 5, Joven, number 6, June, number 7, Mark, number 8, Vin Sanchez, number 1 again, Joy, number 2, Joyce, yeah, and then Victor, number 3. So 3 mean y equal to a b times exponent x. Okay. Use this here. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8. Okay. So try to understand. So I give you example a while ago, number 1 already. So this 2. Using this data, yeah, using this data. This one. So you just type this data, okay, and then you do. Okay. So the result is already here. So all you need to do is to check the transformation and to understand this. Yeah. Okay. Yeah, this is next. Using this data. So use different non-linear model. 1 to 8. Is the instruction clear? Right. So you can start to see that we can go beyond Excel, isn't it? So Excel only provides a few model, but you can go beyond that. So you can actually derive your own model. How do you know which model? Then you plot. Okay? Based on the plot, if you know the function of that plot, then you can guess. Okay? What function you want. Oh, times. Okay. Right. And once you finish, can you share your screen? Maybe a few. let's continue this next meeting then. Okay, do it on your own so that you can finish. Okay. And then next meeting you show me, yeah? It's only so this video is recorded, so I remember who will do what. Okay. So maybe you get more time. Okay. It's not assignment, so but please show next meeting for your recitation. So thank you for today in that case. Yeah. So see you next meeting. Okay. I hope this is useful. Okay. Next meeting, please before next meeting, please read the slide of this transitional transfer planning, especially the matrix side. Okay, because I hope through this you can start to see the benefit. Okay. Especially when you start to do the assignment of this forecasting, then you can start to see, oh, I can do something beyond, you know, what Excel can do. I hope this is useful. Yeah. Thank you. Yeah. Thank you and see you. Yeah. Bye-bye.
Thank-
Okay, go.
May share, so I won't share
Sure,
any more
sure.
lessons.
Okay, you don't need to next time. Go if you want to share now.
Here, sir. So I do the based on the table, sir. That the x prime is the square root of x. Is it visible already, sir? My
Yeah,
Excel.
okay. Okay, let me open this.
Yes,
So
sir. There's the
what is
given.
your model? Can you write down the model?
The y is equal to a plus b square root of x.
Y is
Yeah.
equal to
Wait, sir. I'll just paste. Here, sir.
square root. Okay. So in that case,
I just based on the
okay, you
table,
get
sir,
square
that
root. Correct. That's your square root x.
the
Huh?
only x is the square root, while the y will
Okay.
just
You're,
copy.
you're so lucky. This is so easy.
And alpha is also a and beta is also b. So I'll just
Yeah,
get the uh what do you call this equation of the linear
right.
of the plot of x and y prime. Then here's the based on Excel already, sir, the plotting, the scatter plot. Here's the equation, then alpha and beta. Yes. This is
And
already the alpha and beta. I will just plug it here, sir.
okay.
That's the equation, sir.
So you get 9 and 0.
9.1502
Okay,
and
that's correct.
negative 0.1425.
Okay, that's correct. Yeah. So nice. Thank you.
Thank you, sir.
Thank you. Joben, try to do
Yes, sir.
something else, not just issue. This is too issue for you.
Okay, sir. What number, sir? Or I'll do
Any
F1.
of that. So you can try the one that more the thing
Okay,
that
sir.
you
I'll
think
just
is
do all, sir.
difficult. Eh?
I'll just do all the model.
Yeah. Try to others.
Okay, sir.
Thank you. Thank you.
Thank you, sir.
Yeah, Vin, you want to see?
Sir, you mentioned on how I can claim my recitation.
Eh? Pardon me? What do you want to say?
Yeah, claiming the recitations.
The recitation go to Moodle in the top.
So I put there the total per week. Or
Yes, on the top, you
cumulative.
put the total per week, and then the one that you did not claim, you please reclaim it last time.
Okay.
Okay,
So basically, sir, if I'm I'm logging in on time, that's 1 point already per week.
correct. So
Okay.
I wonder why people don't claim. So
Okay. So from the first class to
yeah,
present, that's
you
1
can
point.
still edit until the end of semester anyway. So no
Okay.
problem.
Then 1 point each, sir, for each recitation instance.
Each recitation, you type, okay, what was your recitation, and then You type there, and then each point, then how many points in a day? So you can claim up to 10, isn't it? Per week.
Yes, sir.
Oh,
Yes, sir. Maximum of 10.
yes.
Okay. Lastly, sir, I'm having trouble with the assignment on pedestrian.
Oh, okay. You want to share what is your problem?
Uh, Actually, it's the algorithm on the shortest distance. Or are we required to do that?
Algorithm shortest distance.
Here, sir.
And
It's my Excel showing. I'm trying to replicate the exercise presented on class. So the vertex
yeah.
from 12 vertices, then the edge flows.
Okay.
Yes, sir.
Yeah.
The
Okay. Go to if you have a problem with shortest path, go to the model. Okay.
sir.
I think we have it after the Regression. After that classical transport demand analysis assignment, there's a slide on shortest path. You can probably use that.
For this one, so that I can automate this matrix.
This is basically path. Yes, you can automate this matrix, and you can do what is called a float Warshall, or you can use the one in path matrix a while ago. In the network structure, do you remember the lab? The lab network structure a while ago? Do you remember? This I'll give you the link if you want. In the Zoom.
Please, sir, even on the chat, so that we can study.
Let me go to everyone. Do you remember the network structure lab a while ago?
The IFN structure.
Yeah, the network structure. So that lab contain path matrix.
As the network, as the output matrix, sir.
Yeah, that's the shortest path distance.
Okay.
So
which one should be my input? This one, the distance matrix,
yes, the distance matrix you
or
need to input.
the distance matrix?
Yes.
Then the path would be the shortest distance.
I guess so.
The gateway.
Yeah. For the path. Yeah. So let's try. I forgot. So I'm not sure if that path represents the number of links or actually the distance here. But you can try. Okay. Yeah. The shortest distance matrix is
This one is
basically.
the
Sorry.
yes, sir. Because this assignment is the harder one than the
Really?
than the network structure and utilization. The one we did in class earlier.
But this one you can count manually. It's only 8.
That's why. That's why I'm asking. I don't want to count manually.
There is an algorithm called Fjord Warshall. Floyd Warshall. Let me search.
Yes, sir. But when I am researching about this algorithm, they use C++ or Python to do this.
Oh, yes, you can use any. Okay, so
Sir, the network structure and utilization lab relationship.
okay. So
And my input,
why you are afraid of Python?
sir?
Why are you afraid of Python? Is it because it's snake?
No, sir. I'm more familiar with C more than Python.
Oh, then it's fine then. You can use C. C is also the algorithm of log Warsaw is only like 5 rows in C.
Then I input the
Yeah.
distance matrix as an
Correct.
array to the C++.
Correct. And then you can get the whole things.
Okay, sir. But yes, sir. I'll try that. Also the INF, IFN.
So it should be no problem. Uh Nowadays you have AI, so you can even ask the AI,
To hold.
to code. Because these are like common already, like for partial is very common, right? So I mean not new, right? So it's already established. That means AI can do for you. Yeah. AI is still very hard for doing real research because something new that not common. Okay. But something that already common, you can just ask.
Thank you, sir.
Thank you. Yeah. So I hope this is useful. Yes, Glenn.
Sir, last one po. Before, when I was doing the first assignment on IFN, I can't make the ideal flow add-in work in Excel. So what I did was I snipped from the Moodle and then manually inputted the information on Excel when I submitted my assignment.
Oh, that's fine.
Um,
Can you get the same result or not?
it has the same result except for the ones that are not read by Excel because the add-ins don't work. Um, I still tried to make it work, but there's a prompt that says you can't use it in protected view, and I can't uh disable the security.
Hmm? You want to share your screen so that we can disable the security.
Of course. There.
Uh,
When sorry, this was the example earlier.
let, let's go
What?
to the Explorer, Windows Explorer.
Sorry.
You go to Windows Explorer. Can you share the screen that you can go to Windows Explorer and then open the add-ins file? You do right click.
Okay.
Okay, that one, right? So right click on that. Okay, show more. And properties down at the end. Yes. And then in general, oh, I cannot see. It,
I have to unblock this one, sir.
correct, you unlock that one. Okay. Then you can you already unlocked that.
Yes, sir.
Yeah, okay.
Sorry, is my screen showing?
Yeah, no, your screen I cannot see that unlock. Anyway, so once you see that, you can either put this one in the actual file or you can just browse this from Excel. You can go to add-ins and then browse this one. Or you can put this in the actual folder of add-ins. Yeah, if you read the documentation, I give you the where the folder of add-ins of Excel.
Yes, sir. I'm trying to open the one that you submit.
Okay.
that you shared with us, and it still does not apply.
Oh, really? Oh,
Yes.
can I see the screen? So it doesn't apply. That means, okay, so can go to file, options, okay, add-ins, go there, click OK. Did, uh, did you get it from, can you browse first, maybe?
This one,
No,
sir.
a while ago. This one is, see, okay, can you see, this is wrong because this is in my folder. Can you see this? User card D, you need,
Oh, this one, sir. So I
uh,
have to change this one
um, enter,
with that.
yes. Okay, just delete the others. So, or you can try this, okay, in any cell that you did not put, because if you have an array, you cannot change that, so you need to delete first and then you type. Okay, but you can put in any cell, for example, in U or V there, okay, and then escape first, and then go to U or V there, okay, and then N and just, oh, there, it's working. You.
Oh, okay. So, sorry. Let me just.
Just tap. You just tap. No need to tap. Use your tap
Hi there.
button. There. There. So you put that.
There.
See?
Okay.
Okay.
Because I was trying to unblock it several times, but it didn't work. I don't know what happened this time. But
Okay, good. Okay. So I don't know.
maybe I did something different from the ones you instructed.
Okay.
Thank
So
you, sir.
thank you. No problem. So uh, now it's working. So I'm also happy. Okay.
Thank you, sir.
Yeah, you can also draw the network there in Excel. You can check the manual.
Okay. Yes, sir.
I hope this is useful.
Yes, sir. Thank you po.
Thank you. So thank you very much. Can I close this?
Yes, sir.
Yes, thank you, Lynn.